I would like to put the camera slightly lower, but this is kind of in position. The ratio test. I hope you can read that. I'm going to try and write bigger. So anyways, this is another test for series convergence. I'm glad I wore this slightly respectable looking shirt so that when you see my arm there, I look like a respectable professional. Another test for series convergence. And it's based on the idea behind the geometric series. So just to refresh our memory, the geometric series is one in which each term has the same ratio with the previous term. So for example, here's one example. There are, of course, many ways you can do this, but here is one example. Oh no, my phone is going to auto turn off. Am I still going? Yeah. So the geometric series is one in which each ratio of an plus 1 divided by an, that is the next one divided by the previous one, is the same, right? This is what a geometric series is. Each ratio like this is the same in a geometric series. And then remember, the way we tell if it converges or not is if that ratio is in absolute value less than 1, then it converges. And if that ratio is in absolute value greater than 1 or equal to 1, it diverges. So this is just refreshing our memory. If the ratio is in absolute value is less than 1, it converges. And if the absolute value of the ratio is greater or equal to 1, it diverges, right? This is all just review about the geometric series, okay? We know all of these things. I hope you can read that. This one is terrible. That one is a little better. I will again try to write bigger. I forgot that I was going to write bigger. All right. Now, even if, so the ratio test is based on this same kind of idea, but in the situation when the R is not the same every time. All right. That's the hallmark, the basic property of a geometric series is that the R is the same every time. Each term divided by the previous one is always the same. What if they're not the same every time? You can still do something like that same idea. So if these ratios are not all the same, a similar thing is still true. Similar thing still works, and I will tell you what it is. This ratio, so I'm also going to look at this, an plus 1 over an, and I'm also going to look at the absolute value of that ratio. Remember, when you take that R, what determines convergence is the absolute value of R. So this says an plus 1 over an, and I'm going to take the absolute value of that. And in a typical series, this will be different every time. But this sometimes still has a limit. So in the ratio test, we look at this. The lim n goes to infinity of the ratio, absolute value an plus 1 over an. All right? Because those ratios are not always the same, you can't just talk about it as if it were a single number, but you can take the limit. And that limit, it may or may not exist, but if this exists, they call this L in our book. It plays the same role as that ratio. The problem with the ratio is in a normal series, in an ordinary series, the ratio is not one particular number. But if you take the limit, then you do get one particular number. And the ratio test is the same thing. It says if L is less than 1, then it converges. The idea behind this is, even though the series is not geometric, if this ratio limit exists, then it more or less is kind of like a geometric when you take the limit. And so its convergence, when you take the limit, will be the same as the geometric. So I'm going to write this as a theorem. It's called the ratio test. Maybe I'm going to see how big I can write here. Theorem, the ratio test. My ordinary handwriting is very small. To compensate for my, oh no, my phone just turned off, sorry. I'm going to see everything on my phone for a moment. I'm just going to go in my settings and turn off my display thing here. Here, auto lock is on 2 minutes. I switch to never. You see all that? Oh no, it's off the side. Great. So you won't see my incriminating texts. I don't really have any of those. I'm working on it. I'm not important enough to have incriminating texts. My life is not interesting enough. All right. Okay. I think we're good now. The ratio test. It is about the limit of that ratio. So I'm going to say let L equal this limit. The limit n goes to infinity of the absolute value, an plus 1 divided by an. Right? In a geometric series, those values are always the same, but ordinarily they are not always the same, but you can still take the limit. Now, this limit might not exist, but, and if it doesn't exist, then you just can't use the ratio test. Anyway, what it says is, it's sort of in 3 parts. So, part 1 says, if L is less than 1, then the series an is convergent. In fact, it's even better than that. It is absolutely convergent. Absolutely. That's a U there. Absolutely convergent. And I will just say in parentheses, therefore convergent. Therefore convergent. If you recall from last time, we talked about absolutely convergent. It means when you take the absolute values of all the terms, it converges. And we talked about the fact that if it's absolutely convergent, then it automatically is convergent in the ordinary sense. So if the L, that ratio in the limit is less than 1, then the series converges. If the L is greater than 1, then the series diverges. And unfortunately, there's a third case. If the L equals 1, actually in that case, you don't know. So the ratio test has this kind of failure case. If it turns out that that limit actually equals 1, then actually the ratio test is inconclusive and you just have to do something else. So this is not really another case, but it just says if L equals 1, then inconclusive. The ratio test cannot be used in this case. I will just say in parentheses, use another method. But I think you'll see as we do some examples, the ratio test is actually quite easy to work with. And so, you know, to me, this is like one of the first things that I would think of when I'm looking at a series and trying to decide if it converges or not. The ratio test is a great sort of starting attempt because it works out fairly easily, unless you get L equals 1. Then it didn't work and you got to do something else. Sorry, I meant to say sort of in this case right here, if L is greater than 1, in this case you should also say, I'm not able to squeeze it in very nicely, or L equals infinity, that counts as being greater than 1. This is probably what you would think. But you know, this limit up here, it can be that this limit is infinite, right? Because it's a limit, and that would still fall in under case 2. So if L is greater than 1, you know, if the limit is actually infinity, that counts as being greater than 1. That's all I'm saying. Infinity is greater than 1, certainly. Everybody knows that. All right. Let's try some examples of this. Are any questions about that so far? I hope everybody can see and read what I'm writing. I'm trying to say it all out loud too. All right. Some examples. How about this? The ratio test is especially good when you have some kind of mixture of n inside the exponent and also n not inside the exponent. This is a typical example like that. We have the n is inside, this is n divided by 2 to the n. So n is inside the exponent in the denominator, but in the numerator, it's just sitting there by itself, all right? If it were just 1 over 2 to the n, that's a geometric series with r equals 1/2, and so it converges. But n over 2 to the n is another deal. All right? As usual, I want to know, does it converge? I'm going to do the ratio test, which involves the lim n goes to infinity, absolute value an plus 1 over an, right? This is what you need to check for the ratio test. If this limit exists and is less than 1, then it converges. And if it's greater than 1, it diverges. If it equals 1, we got to do some different way, but it's not going to equal 1. Let's just do it. I mean, you can pretty much just sort of plug stuff in here. An plus 1 on the top. So I have lim, all right. Absolute value. Absolute value is sometimes a pain to deal with, but usually everything's going to be positive anyway, so it doesn't matter. An plus 1 is in the numerator of this fraction. That means I go up here and I replace, so this, what's written here is an, right? So to get an plus 1, well, maybe I'll write that in the denominator first, right? N divided by 2 to the n. That's an. What is an plus 1? You got to go here and replace all the n's with n plus 1. Anybody want to say what would that look like? N plus 1 over 2 to the n plus 1. Great. All right. And now similar to kind of what you saw when we did like that limit comparison test, this is, you should feel like it looks similar to the limit comparison. We have to like rearrange this fraction. First of all, can I say the absolute values, we can just get rid of them at this point because everything inside there is all positive. So I don't need to worry about the absolute values. And let's simplify the fractions. The way I usually do this is I'll write the numerator and then times the reciprocal of the denominator, like that, right? This is the limit I need to take. I have n plus 1. Let's sort of put the exponential parts together and the other parts together. N plus 1 over n, and then I also have 2 to the n over 2 to the n plus 1, right? N plus 1 over n, and then 2 to the n over 2 to the n plus 1. Can we handle them separately? I think so. What is 2 to the n over 2 to the n plus 1? Anybody, can you see how to simplify that?
With the top of the fraction, 2 to the 2n to the n plus 2.
Oh, are you distributing here?
Yeah.
So that's correct what you just said, although I think not very helpful. I think it's better to keep this thing separated because this fraction right here can simplify.
Why'd you switch the denominators?
Did I change it around?
It was n plus 1 over 2b n plus 1.
Yes. Yeah. So these are multiplied.
Yeah.
So you can move, move things around the order. And I did that because this can actually, when you put it together, you can simplify that. Any ideas there?
The bottom one would be 2 to the n times 2. There's something, you can pull out a 2 to the n somewhere.
Yeah, actually, it is true what you said. The bottom, 2 to the n plus 1, actually, that's the same as 2 to the n times 2, isn't it? Because of the way that exponents work. What we're looking at, 2 to the n over 2 to the n plus 1, is something like, maybe 2 to the 7 divided by 2 to the 8. You can cancel all those 2's, and there's going to be 1 left over on the bottom, right? Because there's one, if you think of this as a product of a bunch of 2's, 2 times 2 times 2, they all cancel, except you had 1 extra 2 on the bottom. So what do you get from that fraction? It ends up being just 1/2, right? You have an extra 2 on the bottom. All the other 2's cancel. So this is lim n goes to infinity, n plus 1 over n times 1/2, right? Isn't that nice? Those exponential parts are the parts that kind of I start to worry about when I'm thinking about the limit, but they actually totally cancel. So all I got to do now is just the limit of n plus 1 over n, but that you can just like divide by the biggest power of n, that simple trick, right? So when we do that, still see down here? I'm going to divide out n on that thing. So lim n goes to infinity. It's going to just be 1 plus 1 over n over 1, right? I divided on top and bottom everything by n. And then, of course, still 1/2 here. And we take the limit. That 1 over n inside the fraction becomes a 0 because n is going to infinity. And I just end up with 1 plus 0 over 1 times 1/2, which is 1/2. All right, and so, see if I can just continue. So L equals 1/2. It's less than 1, so it converges. Right? The end. Any questions about that? What are your questions?
Would you get the 1 to plug into n?
Yeah, this here, going from here to here,
Yeah.
I divided the whole fraction out by n on the top and the bottom.
Okay.
So this n becomes like n divided by n, which is 1. This becomes
Oh.
1 divided by n. This becomes 1 also on the bottom. Refocus that. I don't know. All right. So this is a typical example using the ratio test. I got one more. I have some for you to try also, but actually before that, I said there were 2 tests. The second is just a simple variation of this one. I'll tell you both of them before we have some for you all to try. Okay, let's try. Here's a slightly crazier looking one. Minus 1 to the n, e to the n over n to the power 8. All right? Again, this has some kind of mixture of n's inside the exponent mixed with things that look like n's n's to some power, right? Some of these have n inside the exponent. Some are just n to some power. Don't need to think about it too much. Let's just do that limit, like set up the big fraction. You know, the way that this usually works out is you make this big fraction. Hopefully a lot of that stuff will cancel out, just like the 2 to the n's canceled out in the previous example. And then hopefully you can take the limit without too much problem. Let's just try it. So I'm going to say this L, it's the lim n goes to infinity, absolute value, an plus 1 over an, right? Plug it all in, you get some kind of big and nasty fraction. I can handle that. It's going to be lim n goes to infinity, absolute value. Okay, on the bottom, you just write an exactly like it is. It's going to say minus 1 to the n, e to the n over n to the 8, right? That's an. Sorry, this is very hard to see on the screen here. I'm going to try, I can zoom in if my mouse works. There's a mouse on this deal. Give me a moment here. I hope this will be worth it. We'll see. Sure, while I'm wrestling the mouse. Mouse wrestling. Is that better? Yeah, I think so. I can crop out the table too. Look like more. I have to just make sure I stay inside the lines. I think that's better. Okay, what do we got? On the bottom here, I just copied the original thing. On the top, you copy the original thing, but you use n plus 1 instead of n. So it's going to say minus 1 to the n plus 1, e to the n plus 1, divided by n plus 1 to the power 8. Make sure you're just plugging in where it used to be an n. You are changing it to n plus 1. So like on the bottom there, it's easy to mess up a little bit. N to the 8 becomes n plus 1, in parentheses, to the 8. All right. Let's continue then. How can we simplify? So I'm going to write, as I usually do, write this big fraction instead as a multiplication. I find that's the easiest way to simplify. It says minus 1 to the n plus 1 e to the n plus 1 divided by n plus 1 to the power 8 times the reciprocal of the other part. N to the power 8 on top, minus 1 to the n, e to the n. All right? And hopefully a bunch of stuff will cancel. Any thoughts about the absolute value signs? You know, ordinarily I like to get to a certain point and then just say, all right, I'm going to ignore the absolute value signs because everything is positive. What do you think?
We have to keep it because
Yeah, the absolute value signs, they do kind of matter in this example, although I really would not like to keep them there. In this example, actually, you can kind of simplify them away somehow. Anybody have an idea? Like, you can actually do the absolute value, you know, yeah.
it was the negative one that we you can like flip the fraction like we did before, and the negative one should cancel
Yeah,
out. Some,
yeah, there's some cancellation among the negative ones. Actually, there's an extra negative one in the numerator than there is in the bottom. So you could cancel them and just end up with a single negative one in the top. But anyway, when you do the absolute values, so that means actually the thing on the inside is negative. But when you do the absolute values, it turns them positive. So can I just say, like, the absolute values are going to kill those minus ones. It doesn't even matter what they end up being. If they end up being positive or negative. They just all get wiped out, and everything else is going to be positive. So the effect of those absolute values, I'm not going to write the absolute values anymore. And I'm also not going to write those minus 1 to the whatevers, because the absolute values will just wipe the signs away, right? Everything becomes positive. Where it used to be negative before, it's now positive. All right, let's try and simplify this. So I'm going to do the same trick like I did before, and that is put the sort of similar looking things together. So I'll put the e's together in the same stack and the n's together in the same stack. So it's going to say, try and keep this on screen. Let's put the n's first. So n to the 8 over n plus 1 to the 8 times, and then e to the n plus 1 over e to the n. All right, here I have a product, a bunch of e's on the top and a bunch of e's on the bottom. What does that end up being after we cancel all the e's that we can? Just e, yeah. You have one extra e on the top. Everything else will cancel. And so we end up with just e. So that second thing is just e, the number, you know, e is a number, right? So just the number e. All right. N to the 8 over n plus 1 to the 8. What are we going to do with that? My typical approach would be to, maybe this would be better if I zoom the camera. Then everything is super big. And whoa, didn't want to do that. I'm not going to mess with it. N to the 8 over n plus 1 to the 8. Ordinarily, I would divide out by the biggest power of n. And actually, you can still do that. I'm going to divide the top and the bottom by n to the 8. This makes 1 on the top. It's a little... Oops. There should be no bar there. Lim. N goes to infinity. I'm dividing the top and the bottom by n to the 8. On the top, I get 1. Because n to the 8 divided by n to the 8 is 1. What happens on the bottom? This is really like 1 over n to the 8 times n plus 1 to the 8 times e, right? And this is a little strange, but what you can do here is you can actually shove this n to the 8 inside the parentheses here, and it becomes an n. This is similar to, sometimes you see like when you pull a number either into or out of a square root sign, it either gets squared or gets square rooted. Here I'm pushing n to the 8 inside of the 8th power, and it becomes just n when it goes inside the 8th power. So this is the same as 1 over n plus 1 over n to the 8, isn't it? Actually, you know what? It occurs to me now. Sorry, this is not wrong what I just wrote. Although there's a much easier way to explain all this. Would you mind if I just scribble out a few of these steps? Here's the better way. As I was writing up these notes for myself, I did it this way at first, and then I realized there's a better way to do it. And so I redid my notes, but then I fell into the same old habits. This is not wrong what I wrote, but actually there's a better way. Check it out. From here, here's a cuter and easier way to think of this. Turn this into lim n goes to infinity. N to the 8 over n plus 1 to the 8 is this. N over n plus 1, the whole thing to the 8. All right? Times e, of course. And then that thing on the inside, you divide the top and the bottom by n, just like in the previous examples. So it looks like, sorry about that little diversion. You divide, on the inside of the fraction, divide the top and the bottom by n. I got lim n goes to infinity. Inside the 8th power, it's going to say now 1 over 1 plus n, all to the 8, times e. And then when we can take the limit. That little 1 over n becomes a 0, and the rest inside the parentheses there is just going to be a 1. So this becomes 1 over 1 plus 0 to the 8 times e. All of that stuff to the 8 is just 1 to the 8, which is just 1. So the whole answer is e. All right? This is what you get when you simplify that limit all the way. What does this mean about converges or diverges? That's the whole point of this example. What do you say? I'll write up a little in conclusion. So I'll line this up here. So L equals E. So that means it converges or diverges? It diverges. Remember, if L is greater than 1, then it diverges. And I suppose you have to remember that the number E is greater than 1. It's 2 point something something. I don't know the digits of E, but I know it's around 2. L equals E. So I'll just say, just for clarity, so L is greater than 1, so it diverges. This is the ratio test. All right. I thought we should let's just do one example where the test is inconclusive. Remember I said in the case when you get L equals 1, then that means actually the ratio test doesn't tell you the answer. It doesn't tell you anything, and you just have to do things by some other means. How about this example? I'll just tell you as a spoiler. This one is not going to work, but I just want to show you a case where it doesn't. This is actually we already know about this series. This is the P series with P equal 3. And so because we already know some stuff about the P series, we know that this converges. A series that looks like this, when that exponent is the P, and if the P is greater than 1, then it converges. But I want to try to see what happens if we do the the ratio test, right? What happens if we do the ratio test? So let's try the ratio test. We got to do the same old thing. The nice thing about the ratio test is you don't really have to think too much to do it. Some of those other ones, like the comparison test, you got to kind of look at it and figure out, what am I going to compare this to? The ratio test has none of that. You just write it down and see if it works. You don't actually have to have any ideas, or you don't have to come up with a strategy, really. You just try it out. Anyway, this is the limit you get. As usual, I'm going to rearrange this double fraction action here. All right, inside. Okay, do you agree the absolute values are not necessary here? Everything is positive, so forget the absolute value. I am going to write the fractions. All right, it's 1 over n plus 1 to the 3 times n to the 3 over 1, right? I reciprocated the denominator. Might as well put all of that together. It says n to the 3 over n plus 1 to the 3, all right? And then, just like in the previous example, I'm going to sort of pull that exponent of a 3 around everything. So this is the limit of n over n plus 1 to the 3. When you're doing the ratio test, you see things like this all the time. And you may have noticed in the examples, all the examples we've done so far, they involve a fraction that looks like this. It's because you're always dividing n plus 1, an plus 1 divided by an. You will often end up with something that looks like that. Anyway, the next thing, we divide the n on the top and the bottom, just like in those other examples. So I go 1 over 1 plus 1 over n to the 3. I take this limit, and what do we get? We get 1 over 1 plus 0 to the 3 equals 1. And this, when you're doing the ratio test, this is the worst case scenario. If you get 1, it means the ratio test cannot tell you if it converges or not. And you just got to go back and do it some other way. All right? So I'll just say inconclusive. That's the worst. The worst thing that can happen is you went through all that work and you still don't know. All right? Any thoughts about this? This is the ratio test. Okay, let me tell you the simple variation on the ratio test, and then I got some for you to try, and then maybe we'll talk a little bit about the next section. So, one last test. It's actually not really a variation. It's kind of a different idea, but in practice, the way you do it, it ends up looking kind of the same, and so it's easy to sort of lump them together. The last one is called the root test. The root test. This involves, instead of taking ratios of the terms as you go down the list, you take increasing roots. This is a little weird, but I'm just going to write the theorem. This is called the root test. Root as in, square root or cube root or whatever. You're actually going to do higher and higher roots of the terms. Sorry, first of all, it has the same kind of L situation as before, and this is a limit, but instead of dividing each term by the previous one, it is a limit of taking increasingly big roots. So it is the nth root of absolute value a n, the nth root, all right? This is another way to try to detect a geometric series, because a geometric series, well, I'll tell you the root test first, and then I'll try to explain what this comes from. But L is that, okay, and then the conclusion is actually the same as in the ratio test. Again, if the L is less than 1, it converges. If the L is greater than 1, it diverges, and if the L equals 1, you don't know anything. So if L less than 1, then the series AN, and in fact, again, the conclusion is that it is absolutely convergent, and I will just say, therefore, it converges. But in fact, it's more better. It absolutely converges, but usually we don't care about that. Number 2, if the L is greater than 1, I'll just say, or I'll write it properly this time, or the L is infinity, then it diverges. And 3 is if the L equals 1, then the root test is inconclusive. All right, sorry, I'm off the bottom. Then the root test is inconclusive if L equals 1. All right, this is called the root test. The way you do it ends up being very similar to the ratio test, only you're not making fractions, you're taking nth roots of things. And I'm going to try and explain to you a little bit why you should believe this. It also has to do with the geometric series. What? I just got an email. Yeah. All right. I put it on airplane mode, but it's also plugged by a wire into my laptop, so it's probably not possible to stop. Sorry about that. Good thing I'm not getting incriminating text during class. That would be so embarrassing. Yeah, what does this have to do with the geometric series? It is also all about the geometric series, kind of behind the scenes. Remember, the geometric series, last time I described it, I said the ratio, each one divided by the previous one, is always the same, all right? But another way of thinking about the geometric series is that it just looks like this. It has a and then r to the n, right? That r is getting multiplied by r over and over again. This is another way of writing the geometric series. Now, technically, it's r to the n minus 1, but that really is not very important. Another way you could say this is it is equal to a over r times r to the n, if you just to avoid having to deal with that n minus 1. But anyway, if you do have a geometric series, so if it is geometric, then when you take the nth root of an, what you get is the nth root of a over r times r to the n. Now this nth root of a over r is just a constant. But then when you do the nth root of r to the n, you get r. All right? Sorry, I'm off the bottom. And so what I'm saying is, again, the convergence of this thing is related to this r, and whether it's and so the geometric series will converge when the r is less than 1 in absolute value, and this thing over here is basically a constant times r, and so this thing also is related to when, sorry, this down here should be a r. It's a r in this denominator. It doesn't really matter based on what I'm saying, but yeah, that should be a r down here. This, when you continually take these nth roots in the limit, it eventually becomes 1. When n is large enough, the nth root of any constant eventually becomes 1. And so what you get when you take this limit is just r. So that limit, this L here, in a geometric series, this L basically equals r. And so these properties are what you would expect from a geometric series. For the root test, all we're saying is in the limit, if this L exists, then your series is basically acting like a geometric series. And so all the same convergence properties are still true of your series, even though it's not technically geometric. All right, let's try some examples though. When you're using the ratio test or the root test, you don't really have to think about any of that stuff. But let me just say we use this to be honest, the root test doesn't work all that often. It is useful when everything is inside an nth power. Here's an example. The examples for this usually tend to be sort of very weird. Things like this, where I have an n in the exponent, but is also an n on the inside of the thing which I'm taking the power of, all right? This is kind of weird, and it's a fairly specific situation, which is why we're not going to make such a big deal out of the root test, because it really is only good in situations like this, where you have stuff involving n, which itself is inside of an nth power, all right? This you almost never encounter in calculus. Something like x to the power x is very weird. But sometimes it comes up. Anyway, n plus 1 over 2n to the power n. Let's try this using the root test. So I look at this L, right? It is lim n goes to infinity of nth root of absolute value an. So plug it in. You don't have to do any n's and n plus 1's in this case. You just use an. Nth root of an is n plus 1 over 2n to the power n. And the nth root will cancel the power n on the inside. This is the whole point of the root test, is used in this kind of situation because you want this, you need this nth root here to cancel the power of n on the inside. What happens when you cancel the power of n on the inside? All you get is just that original fraction there. So it now says lim n goes to infinity of just that fraction, n plus 1 over 2n. And now this is an easy limit to do. You don't have any nonsense about exponents, so we just divide everything through by n like we always do. It looks like 1 plus 1 over n divided by 2, right? I divide through the whole fraction on top and bottom by 2. And then I take the limit. That little 1 over n becomes 0, and what's left is 1/2. So L equals 1/2. So L is less than 1, so it converges. Sorry, I didn't even mention that I ignored the absolute value signs. But yeah, in this step right here, I stopped writing the absolute values. It's because everything in these terms are always positive. So you don't have to worry about the absolute values. All right, this is the root test. You use it when you see stuff involving n, which is itself inside of an nth power. All right, anybody got questions about that? I have some for you all to try. You'll see if you understand it or not when you try it yourself. So these ones, I will leave it to you to decide if you should use the ratio test or the root test. Let's try. How about 3n to the 5 over 2 to the power n? How about n plus 5 to the n over negative 2 to the n, and 2 to the n over 12n to the 4. All right, see what you think. I'll give you a few moments. I hope you can read them all. The last one says 2 to the n over 12n to the 4. Zoom it. It's up to you. You'll have to decide for each one which one to use, either the ratio or the root. So no, they're not all the Any questions from the folks at home? Hope you're doing all right. I know these are trying times for the folks at home.
What's the first one you looked at?
The L, you should have got a half.
Yeah, this is a zero dip.
I can start writing in my answers here.
Yes.
Hope you said the second one diverges. All right, it looks like people did pretty good. Let's just go over the second one there, which is about the root test. As I was walking around, everybody did the first one perfectly. Whoa, I'm getting some more text. These are my eBay searches. They're not text, they're emails. All right, I get alerts of things I want come on eBay. Okay, yeah. The first thing in the second one, I mean, you identify first of all that you want to use the root test. That's because everything is inside of an nth power. And then when I do this nth power, I appreciate those of you who thought closely about the absolute value signs. I have absolute values around this stuff. You can push the absolute values into exponents. So really this is the same as absolute value n plus 5 to the n divided by absolute value negative 2 to the n. And so the only effect the absolute values have is the negative 2 downstairs becomes a positive 2. Otherwise, I can now take the nth root of everything, and I end up with just n plus 5 over 2. All right? And taking the limit as n goes to infinity of that, I should have been writing this all along, but the limit as n goes to infinity, n plus 5 over 2, this diverges. In fact, it equals infinity, right? This limit equals infinity. So L equals infinity, so the original series diverges. I hope that's what you said. All right. The first one, you should have used the, yeah.
So for the second one, do you not divide by n since there's nothing in the denominator? Like since there's an n in the numerator, you can just divide it by n.
Yeah, it's not necessary to divide through by n, just because you can already tell that the numerator is becoming infinite, while the denominator is just 2. So, yeah, it's going to be infinite. Yeah. Great. And the third one, I don't know if we need to work through the third one. The third one, you should have said it diverges because the L equals 2. Did anybody get that? Sorry. Yeah, 2. I agree? I think some people agree at least. Yeah, if you work out the third one there, it diverges because the L equals 2. All right, this is the root and the ratio tests. And that's the end, actually, for our long journey with the convergence tests. We spent a couple weeks on that stuff, and that's it. We've got about 15 minutes to go for today, so I think we can start talking about the next section. Is that all right with everyone? I didn't. You want to? Yeah, we can do it, I guess. I said out loud the limit is that L, you should have got 2. Let's see if we can do it. So the third one, you use the ratio, 2 to the n over 12 n to the 4. All right, so the ratio is going to be absolute value an plus 1 over an. So we get an plus 1 is, sorry, lim still, 2 to the n plus 1 over 12 n plus 1 to the 4, and then divide by 2 to the n over 12 n to the 4. Sorry, my pen is not great. And then we do the old fraction thing. Went too far there. The thing with the fraction is it becomes 2 to the n plus 1. Let's just gather, after gathering the 2 to the n's together and then the other parts together, it's going to be 12n to the 4 over 12n plus 1 to the 4. I think once you simplify stuff, it ends up looking like that, rearranging the fractions properly. And then this, I can cancel the 12s. And then the 2's will cancel out. I have an extra 2 on top, and so that part becomes just 2, all right? And then times n to the 4 over n plus 1 to the 4, I will write this way, n over n plus 1 all to the 4. And then that part, n over n plus 1, when you take the limit, becomes 1 in the same way that it always does. So this is lim, you do the same old thing, 1 over 1 plus 1 over n to the 4. This becomes 2 times 1 to the 4, which is 2. And so the L that you're looking for equals 2. And so it diverges because the L is greater than 1. That's it. The ratio test gets the job done, at least sometimes. All right? I like the ratio test, like I said, because you don't have to really have any big ideas. You just plug everything in and see what you get. All right, let's go on to the next topic then. And actually, this is one of my favorite topics in the course. It's a fitting end to the course, I think. This is more or less what we're going to be talking about until the end. It is, because it's kind of a big deal. The topic is, trying to line it up perfectly. I got to get a new pen. Power series. A big deal from a theoretical point of view, but also like from a practical point of view. This was extremely useful in the real world when power series were discovered around like the 1800s. Suddenly, mathematicians were able to do computations using power series, which really had been impossible to do beforehand. Things like computing digits of pi or digits of the square root of 2 or something like that. Power series was a major game changer when people discovered how to work this out. Anyway, but we're not going to get to any of that today, but just the very basics today. So a power series, I'll tell you the definition. A power series is like a series in that you are adding together infinitely many things, adding them all up. But what makes it a power series is that it has like variables in there, which are powers of x. So it's, I'll say it's like an infinite polynomial. Something like, we write it as if it were a function. Like this. Just like a polynomial, it has a constant term, it has a x term, an x squared term, an x cubed term, but it goes on forever. That's what's different between a power series and a polynomial. A power series is like a polynomial that has infinitely many terms. Of course, we are typically going to write this as a series, like using the summation. Cn x to the n. So the terms, each term looks like some constant times the power of x. And those Cn's, as you might imagine, are called the coefficients of the power series. The Cn's are the coefficients of the power series. Naturally, that's what we're going to call those. The coefficients, all right? And we think of a power series like a function, where you can plug a value in for those x's, and then for each different value of x, it'll all add up to something different, all right? So we think of this, I'll just say this works like a function in the sense that you can plug a value in for x and get an answer, right? So this power series works like a function. But what's different from this and an ordinary function is sometimes it might converge and sometimes it might diverge, just because it is a series, and we all know that sometimes a series converges and sometimes it diverges. So I'm just going to say this works like a function, but sometimes, and what I mean when I say sometimes, I mean for certain x values, announcement from the dean's office. Sometimes, that is for certain x values, it diverges. So this is like a function where you can plug in any x you want and you get an answer, although sometimes the answer is just, it diverges. You don't get a real answer, all right? This is a power series. Okay, here's a very simple example. Maybe the simplest possible example of a power series would be when you choose all those coefficients just to be 1 every time. So if Cn equals 1 each time, then the power series I'm talking about would just be the sum of x to the n, which if you write out the terms is just this. This is like an infinite polynomial where all the coefficients are 1. I would like to know if we consider this to be a function, then for which x's does this converge, and for which x's does it not converge? All right. Well, actually, if you think of x as being a specific number, this series, as I wrote it, is a geometric series because when you look at the ratio of each one divided by the previous one, the answer every time is x, isn't it? Because you always get like x divided by 1. That's the first two terms, right? Or I could do the second two. X squared divided by x, the answer is x. Or x cubed divided by x squared, the answer is x. Okay, so this actually is geometric. This is a geometric series with r equals x, right? Each term divided by the previous one is x. And also the a is just the first term of the series, which in this case is 1, right? And so if x in absolute value is less than 1, because r is x, right? So it converges when the r in absolute value is less than 1. So in this particular example, if the absolute value of x, which is the same as r, is less than 1, then it converges to 1 over 1 minus x, right? That's the old formula, a over 1 minus r, right? But in this particular example, a is 1 and x and r is x. So you get, sorry, I'm off the bottom. If x is less than 1 in absolute value, then it converges to 1 over 1 minus x. So for example, if f of x equals 1 plus x squared, if I think of this as a function, then what is f of 1/2? Well, 1/2, its absolute value of 1/2 is less than 1. Sorry, I'm off the bottom again. I'm looking at my screen here, but it's a slightly different viewport for some reason than what's on the big screen. Sorry about that. What is f of 1/2? Well, I said it converges to this, 1 over 1 minus x. So this equals 1 over 1 minus a half, which is 1 over a half, which is 2. Right? 1 over half is 2. But, yeah. So it converges to 2. This value is less than 1, which means it converges. And what it converges to is the number 2. If I ask you, say, what is f of 3? That diverges, right? So certain values, it's going to diverge. Certain values, it has an actual answer to it. All right? So the big question, which we are often going to discuss, although this is not the only thing to discuss, it's a big question concerning power series. Given a power series, say f of x, with some, that was just one example I just did, but you could change around the coefficients and you get a completely different power series. Given a power series f of x, you can ask the question, for which x does it converge, right? And for which x does it diverge? In this example that I just did, I said very specifically, if absolute value of x is less than 1, then it converges. So in that example, it's easy to say. But in other examples, it's not easy to say. And this is a big question that we're going to have. If you arrange the coefficients in some other way, then how do you know if it converges or not? Here's another example. How about this power series? 1 over 3n times x to the n. I want to know for which x does it converge? And we are going to use all the same old convergence tricks that we've been learning the past few weeks. In fact, for this one, it turns out that the ratio test is appropriate. So we're going to use the ratio test. Thinking of the entire thing inside the parentheses as an. So I'm going to do this whole thing, lim n goes to infinity, absolute value, an plus 1 over an, right? Plug it in, where the a is everything on the inside. Don't just take this 1 over 3n part, but you have to take everything, all right? And in fact, you'll see why. We want to take the x's also. So on the bottom, this is still an is, can I just write as a fraction, xn over 3n. So this is x to the n over 3n. And on the top, I have x to the n plus 1 over 3 times n plus 1, right? This is the ratio. I will try to simplify the fraction. So I get x to the n plus 1 over 3 times n plus 1. And then the other part is going to be 3n over x to the n, right? Unfortunately, there's not a simple thing you can do with the absolute values in this one because you don't know. Like usually I just look at it and say, well, everything here is positive, and so the absolute values don't matter. But actually, we don't know if x is positive or negative. And so it's not really possible to do that per se. But whatever, let's just keep doing the same old tricks that we usually do, which is I'm going to put together the things at the ends. In fact, actually, the 3's will cancel at this point, right? I can just cancel 3 here and here. And if I rearrange those, just reorder those two fractions, I get n over n plus 1, which we all know that's going to converge, or that goes to 1 when I take the limit. And then this other part here is x to the n plus 1 over x to the n. In absolute value. All right? That first part there, when I take the limit, becomes 1. What is the second part equal? Yeah, just x. I have products of x on the top and the bottom, and there's an extra x on top that's not canceled by anything on the bottom. So the first part, when I take the limit, is 1. These are still inside the absolute values. The second part is equal to x. And so my final answer is absolute value of x. All right? So L equals absolute value x. All right? Now, usually we get a particular number for L. This, I don't know if this seems unsatisfying to you, but actually what that means is I can just say, because we know the ratio test, I can say, so it converges. When does it converge? When L is less than 1. Well, you can say then when absolute value of x is less than 1. All right? And it diverges when absolute value of x is greater than 1. Because it diverges when the L is greater than 1, all right? So that L, knowing the L being less or greater than 1, tells you for which x it's going to converge, because in this case, the L equals the absolute value of x. All right? I think that'll do for now. We'll do a bunch more like this next time. And we'll also talk about the test. And it will be on Zoom next time. Sorry for the inconvenience. See you later.